Hello. Good afternoon, friends. Today, we'll see the block two of this introduction to thin films of elective paper 5B. Uh, Before going into the this what we call thin films, so we will start with the vacuum techniques. So we should know about how the vacuum is created and all those things. So first, we'll start with the unit 5, that is the vacuum techniques. So in this vacuum techniques, we'll see how the vacuum can be produced in different methods, and as well as we will see the measurement of the vacuum by using different techniques like Bourdon gauge, Pirani gauge, and Perning gauge, and all those things. So first of all, we'll see when this what is the vacuum techniques which we have used in starting at starting. So this techniques industry has been started in the early years of 19, 1900, 1900 years. That is in the early 20th century, we can say that. So these vacuum techniques are mainly started using at that time only. So maybe around 120 years back, they have started this vacuum techniques. So commercially, otherwise, we can say that where we have used this vacuum technique is we have used in the creation of this electric light bulb. So in the early days, the electric light bulb, whichever we have used, this electric light bulb is made actually with the help of by the creation of this vacuum inside of that bulb. Okay. And then after starting, we have used in the creation of this electric light bulb vacuum technique is used. And then after different places we are used in the creation of these vacuum tubes and the cathode ray tubes, and as well as this electron microscope. So in the creation of this electron microscope, cathode ray tube, as well as this vacuum tubes, we use this vacuum technique we have been used. So later on, this has been utilized in various applications. It has been used. Okay, with the help of this vacuum creation, that is development of this vacuum technique. So this included like in the what we call lens surface to increase the light transmission, as well as the in the preparation of this what we call blood plasma for blood banks. There we have used this vacuum technique, and as well as the what we call in the production of these metals like the metal which is titanium. The creation of this metal, this vacuum technique is used. Okay, the creation of this titanium metals, as well as I told that preparation of in the preparation of the blood plasma for blood banks and the production of these reactive metals like titanium. In all these cases, this vacuum technique is used, and as well as in the what we call in the maybe in the year 1950 in the nuclear energy also this vacuum technique is used. This vacuum equipment is developed on a large scale, uh, and as well as the to create what we call a very large scale vacuum. Otherwise, a high to ultra high vacuum is applicable in the case of the semiconductor industry in the preparation of this what we call thin film. So when we are prepared any thin film, that has to be done in the vacuum only. So there we required some high vacuum creation is required. That is what we call it as a high to ultra high vacuum creation. We are going to be called there also we'll use this vacuum creation in the semiconductor industry when we use this thin film. So these thin films are having very high applications in the preparation of these thin films. Also, we'll use this vacuum creation. Okay, and as well as in the case of the what we call in the preparation of this microelectronics, also we use this what we call vacuum. So, experimentally, in order to create a perfect vacuum, it is not possible. Means exactly means ideal case. We can say that a perfect vacuum is nothing but ideal case, but one can create almost like extreme case of this vacuum can be created with the help of these vacuum techniques. Okay, so generally, we'll use this vacuum pumps around to create a pressure of around 760 to 10 to the power of minus 13 torr. In between this range, we can create. Okay, so depending upon the ultimate pressure needed in vacuum system, so the combination of different types of vacuum pumps have been used for different applications. Okay, so this is what actually where we used this vacuum techniques, where it has been started maybe in the early 1900 years, and then later on it has been very used in producing what we call thin films as well as the microelectronics. Nowadays, we're using these microelectronics very much in applications we are using. So, in order to create these microelectronics thin films, we require this vacuum creation is required. So, it is very important. And nowadays, we are using this vacuum technique is very essential. So, that is what we have. And if you see how the production of these vacuum pumps we can get. Okay, so that is the production of vacuum pumps. How we get this vacuum, all those we'll see here. That is what we call it as a production of vacuum pumps. Production of vacuum pumps. Right. Right. So a vacuum is created in a chamber or in any vessel. We can create this vacuum with the help of a vacuum pump, which is known as a exhaust pump. We can call. Okay. So vacuum is created in a chamber or a vessel with the help of a vacuum pump known as a exhaust pump. So which can remove this air. Okay, which can remove the air inside, or as well as it can exhaust air, or it can remove the gas or any vapor which is present in the vessel. So it can remove the air or the gas which is present in the and as well as any vapor which is present in the vessel, it can be removed. Okay, so this exhaust pump actually, this exhaust pump, it is consisting of actually two ways it is consisting of. One is we'll be calling it as a inlet it is going to be have, and another one it is having the outlet. Both it is going to be have inlet as well as the outlet. If you take the inlet, this the inlet is connected to the vessel actually, and the outlet is which will expels the air. Okay, inlet is connected to the vessel. This is connected to the vessel. It is connected, and it outlet is which is giving out this what we call whatever maybe the air or gas, whatever is present inside the vessel can be evacuated from there. Okay, so outlet with which expels the air or gas or vapor which is present inside the vessel, that can be had. So this exhaust pump is consisting of two. One is inlet as well as the outlet. The inlet it is having the what we call connected to, vessel. Inlet is connected to the vessel, and outlet is going to be expels the gas or vacuum or vapor, whatever it may be inside of the vessel it is consisting of. Okay, so these are the two parts which is consisting this what we call vacuum exhaust pump. We can say that. Right. So the pressure at which the gas or air is called exhaust pressure, we are going to be called, which is equal to generally the exhaust pressure, which is equals to the atmospheric pressure if the outlet is open to the atmosphere, or it would be less than that low pressure or higher order vacuum in the chamber it is going to be have. Okay, the exhaust pressure should be very small generally. To achieve this, the vacuum pump and the high vacuum pumps are arranged in series. Okay, to achieve this one, backing pump and as well as high vacuum pumps are arranged in series. Okay, so the air or gas or water vapor which is present in the chamber are drawn in at the inlet and of high vacuum pump and expelled out at its outlet into the inlet of the vacuum pump. So finally, it will be coming out, which is expelling the gas into the atmosphere. Okay. So attaining this vacuum is under the minimum pressure and depends mainly on the exhaust pressure and changes from pump to pump. So depending upon the pump to pump, its value is going to be changes. So mainly the pumps are these pumps are classified into different types. They have been classified. So one which is having the name is positive displacement vacuum pumps. We are going to be called positive displacement positive displacement vacuum pumps we have, and the second one which we have is another type is ejectors we have, and next we have the what we call molecular vacuum pumps. Okay, molecular vacuum pumps are there, and we have like a suction vacuum pumps we are having, suction vacuum pumps we have, and as well as the ion pumps. Okay, ion pumps, and also we have the cryogenic vacuum pumps we have. Cryogenic vacuum pumps. Okay, so these all are classified. Different types of pumps are classified into positive displacement vacuum pumps. We have next we have the ejectors. We have molecular vacuum pumps, then sorption pumps, then ion pumps. We have cryogenic vacuum pumps. We have okay. So under this, if you see, we have like a oil sealing rotary and root pumps. We have in the oil sealing rotary and root pumps. We have rotary. So that is actually the arrangement will be in the cylindrical. It has a cylindrical steel rotator or which is located what we call in a cylindrical rotor housing almost touching the stator surface. You are going to be have another in this we have is a root pumps we have. So these pumps without discharge valve, they can move gases by the propelling action of rapidly rotating members are called rotary balls we have. So under this we can this is one type of this what we call root pumps we have. Then we have the diffusion pumps. So generally diffusion pumps are vapor pumps or vapor ejector maps sorry, pumps designed for pumping rarefied gases in high vacuum less than the pressure is 10 to the power of minus 2 tar of pressure you are going to be have. So these we will be calling it as a diffusion pumps. So diffusion pumps are vapor jet pumps or vapor ejector pumps designed for pumping what we call rarefied gas under the high vacuum range. So less than 10 to the power of minus 2 tar of pressures you are going to have. So these we will be calling it as what diffusion pumps we are going to be. This is also one type of the diffusion pumps we have. And then we have the what we call a turbo molecular pumps are there. So in the case of the turbo molecular pumps, generally uh, these pumps works under the principle of that gas molecules can be given momentum in a desired direction by repelling what we call collision with rapidly moving solid surface. Okay, so the rapidly moving surface is a flat disk. In this case, of molecules drag pump and is a series of rotating blades. In the case of a turbomolecular pumps, you are going to be so by moving these molecules, these vertical turbomolecular pumps, you are going to be have. Okay. So next, these are the different pumps we have. Next, we have the cryogenic pumps also. In the case of the cryogenic pumps, generally uh, it removes the gas from a container by condensing the gas molecules on an extremely cold surface in the container. Okay. So very low temperature it is going to be have. So in this cryogenic pumps, we'll be having the what we call the cryogenic high vacuum pumps. They'll be creating high vacuum by freezing the molecules of air into cryogenically cooled surface inside the pump you are going to be having. If you see the working principle of this cryogenics pumps, if you see, so these cryogenic pumps, the working principle is mainly what we call cryo pumps, usually consisting of two internal stages or pump areas we are going to be, have, which freezes the specific gas. That means it will comes down, its temperature will come down. It freezes the specific gas at a set cryogenic temperatures. So the stages are connected to sealed cryogenic refrigerator run by external compressor. The refrigerator cools the stages. So it is going to be cool, very low temperature. It is going to be cooled around the temperature of 65 Kelvin or 100 Kelvin, in between the 65 and 100 Kelvin. At the temperature, very low temperature, it is going to be. So the main function of the pump is to capture water vapor. That is what we have. Then uh, The second stage, it is consisting of a series of metal pumping surfaces which are arranged in pattern, which is designed for a particular applications. So generally, we have nitrogen and oxygen gases can pump at a range of around 10 to 20 Kelvin. That is very low temperature. Okay. This is about the cryogenic what we call uh, pumps you are going to be have, which will create a very what we call vacuum, which we can create. So next we have like a getter pumps under this, which is used to create what we call this vacuum. So we have next we'll go for various types of gauges. So now we'll see the gauges, various types of gauges we are going to be seeing. Various types of gauges we have. Under these gauges are mainly classified into two broad categories. It has been classified. One, it is having the gauges which are total pressure gauges. We are going to be called total pressure gauge. We are going to be called, and second one is the partial pressure gauge. We are going to be have. Another one is a partial pressure gauge. These are the two types we have. Okay. So under this, what we call total pressure gauges, if you see, so we have under this total pressure gauge also we are again we are having different types of gauges. We have like a mechanical gauge. One is a mechanical gauge you are going to be have. So under these mechanical gauges, we will be getting like a Bardan gauge, diaphragm, or liquid manometal, and we have different types we have under this mechanical gauge, and also we have the thermal conductivity gauges are there. Thermal conductivity gauge. Okay. Thermal conductivity gauge. So under the thermal conductivity gauge, we will be having a thermocouple you are going to be get, and as well as the Pirani gauge. These are the two gauges which we have. Next, we have another type of gauges under total pressure gauges, ionization gauges. We have ionization gauge. So these ionization gauge actually, these are the two types we have ionization gauge. One we have what we call hot cathode gauges we are going to be have, and cold cathode gauges. One is a hot cathode gauge we have, another one is a cold cathode gauge. So under this hot cathode gauge, we will be having like a pad, alpha, arbitron, magnetron, etc. We have under this hot cathode gauges. Under cold cathode gauges, we'll be having the Penning gauge, magnetron, inverted magnetron, all under comes under this cold gauges we are going to be have. These under total pressure gauges, we have the mechanical gauges, thermal conductivity gauges, ionized gauges. Under the ionized gauges, we have the hot cathode gauge as well as the cold cathode gauge we have. And if you coming to this next type, that is a partial pressure gauge we have. One is a partial pressure gauge. Under this partial pressure gauge, second one, we have like a mass spectrometer is there, quadrupole is there, and as well as the monopole is there, and monopole mass spectrometers are there. These are the different types. We have mass spectrometer, quadrupole, and monopole mass spectrometers you are going to be have. Okay. So the working principles of these vacuum pumps, their advantages, and we have some limitations. Okay. So we'll see what are those under this. What is the working principle? What is the advantage? Okay. So these are the um, working principle and as well as the what we call advantages and limitations which are there. So coming to this bond and gauge, so these will works under the pressure of this what we call a 760 to 0.5 torr. So main advantage is we can take the direct reading. So, but the disadvantage or limitations which we have under bond and gauge is accuracy is limited. It's exact accuracy it is going to be not going to get in this case. So some limitations are there in the case of this bond and gauge. So that is what you have. The principle which is involved in the working of this bond and gauge is a deflection of a flexible component of low inertia by the force due to the pressure differential you are going to be have. Next, if you go for diaphragm, so under the diaphragm, main working principle is deflection membrane, and advantage is absolute pressure we can measure, but the required thing is under the diaphragm only low temperature is generally possible for high sensitivity gauges. Okay, that is the disadvantage you have. Manometers, if you take the main principle which is involved in this case is the mechanical force exerted by the gas is needed to balance the liquid column. That is what the principle which is there. And direct reading we can take, but the disadvantage which we have for this is difficult to the liquid is oil. Okay, difficult to gauge means guess the if it the liquid is oil. Next we have like Pirani gauge which can be measure a temperature of pressure under 1 to 10 to the power of minus 4 torr. The limitations which we have is the reproducibility depending upon the gas and the suction you are going to be having the case of the Pirani gauge. If you take the thermocouple gauge, it will measure 10 to the power of minus 1 to 10 to the power of minus 3 torr in between. And reproducibility is limited. That is what main disadvantage which we have. Like penning gauge, we have penning gauge can be measure the temperature, pressure under 10 to the power of minus 4 to 10 to the power of minus 7 torr. And the main disadvantage in this case is pressure indication not completely linear. Large gauge pumping requires magnetic field. Magnetic field is compulsory. That is one disadvantage we have in this case. So like this, we have different types of gauges which can be working means under these pressures it is going to be have iron gauge if you take, so this is under 1 to 10 to the power of minus 5 torrs, and conventional hot cathode iron gauge if you take the pressure and the pressure which can be the pressure which can be in between this 1 to 10 to the power of minus 5 we have. So these are the different types of gauges we have. So next, if you see the mechanical gauges, so generally these mechanical gauges, right? So these mechanical gauges, right? So the mechanical gauges measure the pressure. If you take the first mechanical gauges, if you take mechanical gauges, so these mechanical gauges measure the pressure which are from atmosphere to 0.5 torr. Okay, atmospheric pressure to 0.5 torr it can measure. Mainly the working principle of these gauges is that elastic element deforms in response to a change in the applied pressure. That is what the main working principle under this mechanical gauge you are having. Okay, that is these gauges is that an elastic element elastic element deforms elastic element deforms in response in response to a change in the applied pressure. In response to a change in the applied pressure. This is main principle which is involved change in applied pressure difference actually. Pressure means applied change pressure difference. This is the main principle which is involved in the case of the mechanical gauge. So the main advantage of this mechanical gauge, if you take, so the advantages of these mechanical gauges are that their response are independent of the type of the gauge is involved. That is the main advantage which we have. So, and they work on the basis of the force exerted by a gas. Okay, they work on the basis of the force exerted by gas. They measure the total pressure of the mixture of gases and vapors and are called total pressure gauges. We are going to count. Okay. So this mostly in the commercial applications, otherwise in the laboratories, we can say that otherwise in industries, this most common used type we under this mechanical gauge is Borden vacuum gauge and diaphragm type of vacuum gauge. These are the main two gauges which we use under the commercial applications and in industrial applications. These are the two main gauges which we use, Borden gauge as well as the what we call this diaphragm type vacuum gauge. We daily using more. Okay, so if you go for next, that is what we call first we'll see about the Borden gauge. Borden gauge. So in this gauge, the pressure sensing element is a tube we have. So this is the pressure sensing element. Tube is the pressure sensing element, which is sealed at one end and with other end leading to the connection for the vacuum system. So one end is sealed and another end is leading to the vacuum connection to the system. So if you see this, I'll show you this one, the picture of this one. I'll show. So this is the picture of a Borden gauge we have. Okay, this is the picture of this Borden gauge. So one end of the tube is fixed, and another end is open, which is connected to the what we call system here. So if you see that this one, okay, so this side it is sealed here, at this point it is sealed, and another one end of the tube, whichever we have this one, it is can be connected to a vacuum system. Okay, so generally this tube is shape of the tube. If you see, it is elliptical. Okay, the shape of this tube is elliptical. You are going to be have and bent into an arc of spiral. Okay, like this arc of spiral, it is bent. So one end of this tube is rigidly fixed. This is one we have. So a change of pressure inside the tube makes a change its curvature. Okay. So if you change the pressure, automatically it changes its curvature. So the closed end is connected through a system of levers here. So this one, you see, this levers. Okay. So this, whichever we have levers. Okay. The closed end is connected through a system of levers and gates to a needle with which can be moved or a circular arc, circular scale, whichever we have. This one is a this one circular scale. So if any change in the shape of the tube, okay, if any change in the shape of the tube, which activate through the gear system motion in its pointer, okay, so automatically this is going to be changes. So this one is pointer, whichever we have. This one. So if any change here with the help of these levers and gears, it is going to be changed the pointer. So the scale whichever we have, the marking over which the pointer moves. So this is a pointer if it is moving in any side. So where it is going to be marks their point, okay, which indicates the difference between the atmosphere and unknowing pressure. Okay, atmosphere and unknowing pressure. Yeah. So generally, the unknowing pressure X can be get with the help of this PA minus PX. So PX is equals to PA minus PX we can get. So the calibration of the scale is generally based on the inches of mercury from 0 to 30, where 0 represents the atmospheric pressure and 30 represents the what we call a vacuum. This vacuum becomes better as the needle approaches 30. Okay, needle approaches the 30. So commercial gauges around 3 to 4 inches you are going to be having the diameter, and they do not read a pressure better than 0.5 torr. Okay. So, and however, these gauges are normally used to give an indication of the condition of the vacuum system. The variation of atmospheric pressure sets a limit on the working of this Bourdon gauge. So the variation of atmospheric pressure will be limit on the working of the Bourdon gauge. Okay. So if you see the accuracy of the measured value of the pressure in this case with the help of the Bourdon gauge, if you see, it also depends upon the characteristics of the tube material. Okay, and the characteristics of the tube material. So if the tube material changes, automatically the value of this the change in the pressure. Otherwise, the measured pressure can be uh, changes depending upon the material with which you use. So this is about the what we call a Bourdon gauge, which we have. Okay. Next, another type of gauge which measures the pressure is a Pirani gauge. Okay. So next we have is a Pirani gauge. So next we'll see about the Pirani gauge. So generally, this Pirani gauge is made up of a glass or a metal enclosing. Glass or a metal enclosing we'll use for enclosing. A wire is attached along the tube's axis. Okay. So this wire is heated by sending current through it. So by sending the current through it, it is going to be heat up. So the heat, whichever it is produced, the heat energy uh, is primarily spent into three different processes it is going to spend. So mainly, the Pirani gauge is made up of a glass or metal tube, which is enclosing a wire attached along the tube's of axis. The wire is heated by sending the current through it. This heat is producing the heat energy, whichever the heat energy whichever it is producing, it is spended in three different processes. Means it can be spent over three different processes. It is going to be spent. So if you take the first where it is going to be spent, the heat energy is a part of it spending what call in heating the enclosed gas molecules. So inside that vacuum, so it to heating the enclosed gas molecule, heating enclosed gas molecules. The heat energy spent in this part, as well as it can be mm, lost in radiation. Okay, a part of heat energy is lost in radiation. And the third one, where this can be spent, the heat energy spent is due to the what we call the losses due to conduction through the wire leads. Okay, so like this, three different uh, places it can be spent. Right, three different ways it can be spent here. So at low pressures, the energy balance may be expressed. At low pressures, the energy imbalance may be expressed as in the equation as a I square R into I plus alpha delta T, which is equals to CPX, which is equals to CPX into delta T plus sigma into T power 4 minus Ta power 4 plus B into delta T. B into delta T. With the help of this equation, the low pressure, the energy balance may expressed as here. Delta T here is the difference in the filament temperature. Okay, this delta T, whichever we have here. The delta is T is the difference in the filament temperature we have. And the TA here we have. TA is nothing but the ambient temperature. And the PX is the pressure with the pressure within the enclosure we have. Here the C, sigma, and as well as the B, whichever we have, those are the proportionality constants. The C, sigma, as well as this particular B, whichever we have, here is all our proportionality constants we have. And I here, whichever we have, is the current actually. I is the current through the filament actually, and R is the resistance of the filament at room temperature, and alpha is the temperature coefficient of the resistance. Alpha is the temperature coefficient of the resistance for the filament material we have. Okay. So this equation whichever we have written, this also can be written in this form also by interchanging or rearranging the terms. Px is equals to, we can get it as a Px, we can get it as a I square R into I plus alpha delta T minus B delta T minus sigma into T power 4 minus TA power 4 divided by C delta T. By rearranging the terms, we can get this Px is equals to I square R into I alpha, I square into I square R into I alpha plus the alpha delta T minus this value, B delta T minus sigma into T power 4 minus T power 4 by C delta T. This Px is actually the unknown pressure which we can calculate here. This is the unknown pressure which we can calculate here. So now if you see the picture of this what we call Pirani gauge, if you see, right. So this is the picture of the Pirani gauge which we have, this one. Okay. So in this R1 is the filament resistance, which is a variable, sorry, this R1 is a variable resistor. This R2, R3 are the what we call fixed resistors you have. R1 is a variable resistors, and here Rx is actually the filament resistance here. This is actually Rx. It is given that Ri, but not Ri. This is actually here. This is a Rx. Okay. So Rx is nothing but the filament resistance here, whichever we have. This one, right? So R1, R2, R3 is a fixed resistors, R1 is a variable resistors, and the M2 is a power supply. And this R4 is also a variable resistor. R4 and R1 both are R1, both are variable resistors we have. Right. So this is where the vacuum we have to creating the vacuum there. Okay. So if you see the working of this Pirani gauge, if you see, so the working of Pirani gauge is the network which is formed by these four resistors Rx. This one is Rx, R1, R2, R3. So this is the network which is formed. This M1, M2 are nothing but this are the milliammeters where we can measure the current, where we can measure the current here. Okay. So where we can measure the current here. Rx is actually which is made up of a material having a high temperature coefficient of resistance, so that a small change in its temperature will bring out about a marked change in the value of Rx. Okay, so here R1 is fabricated from a material having a low value of alpha here, and R2, R3, if you take, these are made up of materials having the low alpha value and have the same value of resistance. R2, R3 both are having the same value of resistance. So these resistors are made of generally materials like manganium or otherwise a constantinium wires you are going to be have. Okay. So the contaminants in the in the gauge tube is cleaned with the chemicals and they can be dried. Okay. So the pressure is measured here by keeping the filament Rx at constant temperature. Okay, this one Rx. Okay, pressure is measured by keeping the filament Rx at constant temperature. As the unknown pressure changes, the amount of heat withdrawn from the filament changes, and so does it temperature. So now the filament current is readjusted till the filament temperature is brought back to the original value. Okay. The output of balance current involved is measured with a meter and gives the measured value of the pressure. So this is about this Pirani gauge. Okay, this is about the Pirani gauge. Next, we have another type of the gauge, which is a penning gauge. I'll show the picture of that one and we'll see explanation. Okay, so this one. Okay. Right. So this is the penning gauge, penning gauge, which we have. Right. This is the penning gauge. So in this penning gauge, if you see, we uh, it is consisting of a anode. Generally, it is consisting of anode, and this anode will be always between the two cathodes. So this is one cathode, another cathode. In between this, you have the anode. Okay, the anode is in between the two cathodes, and a magnetic field is produced by a horseshoe magnet. Inside the magnetic field is going to produce with the horseshoe magnet. Generally, the magnetic field is perpendicular. Okay, generally the magnetic. Okay, the magnetic field. If you take this magnetic field, is perpendicular to the planes of the cathode and the anode. Okay, so the magnetic field is perpendicular to the planes of the cathode, planes of the cathode and the and the anode. So in this penning gauge, the electrical and magnetic fields in penning gauge are parallel and they are not crossed. However, the potential on the axis of the operating penning discharge is depressed to near cathode potential by the electronic space charge. Okay, so these figures, if you see, so these figures B and C, this and these figures both explain the potential and field configuration inside the penning gauge tube you are going to be have. Okay, so generally it is operated at high voltages around 2000 to 4000 volts. You are going to be apply the potential difference between the uh, anode and cathode. Okay, between the anode and cathode, we are going to apply very high voltage around 2000 to 4000 volts. We are going to be applied between the anode and cathode. With the positive and cathode will be C will be negative. You are going to be have. Okay. The electrons which are leaving the electrons which are leaving the cathode will have uh, will going towards the anode. So, but the magnetic field has the property of forcing these electrons to move in a circle, move in a circle here. So this is cathode, this is the cathode, and in this you have the anode here. Okay, so the electrons which are leaving the cathode will held for the anode, but the magnetic field has a property of forcing these electrons to move in circles. So therefore, the electrons will move in spiral paths between the cathode before finally working their way over to the anode ring. Okay, where these are finally collected. Right. So many electrons will not reach the anode because of inelastic collisions with the gas molecules. The positive ions will be collected by the cathodes, while the electrons formed in the ionization process will break. Means will they'll be behave like the electrons that leave the cathodes. Okay, so the long path of the electrons results in many more ions being formed than if they were able to go directly from the cathode to the anode. So this gives the larger currents and simplify the whole problem of measuring the electrical current. So a small filament is placed behind an off-axis hole in one at the cathode plates. The filament is heated to provide electrons to start the discharge and turned off once the discharge is running. Okay, so this is about actually the penning gauge which we have. Right. So Overall, today we have seen how the vacuum is created. What are the uses of the vacuum? So generally, this vacuum is created at the early 1900 years. At the starting, the application, if you see the bulb which is created, that is based upon the vacuum creation inside of that bulb. So later on, that has been applied for in many applications. And as I told that this can be applied for the application of what we call thin films preparation, as well as in the case of the microelectronics, so in semiconductor preparation of the semiconductor devices. So mainly in the preparation of the thin films, this vacuum creation is very much important. These thin films will be used in so many applications. Okay. So next we'll see about thin film. So what are the thin films where we use these thin films? That is very important. And what are the methods are there this to prepare these thin films? We'll see here. So nowadays, if you see the technology, the present day technology, uh, we will be using this what we call deposition techniques. So this deposition technique is used to prepare the thin films. So which by using this deposition techniques, essentially by achieving the desired properties of the thin films, okay, for their effective utilization of different applications like the microstructure, optical, electrical, and electrochemical properties of thin films mainly depend upon the deposition technique only, and the process parameters employed during this growth of these thin films. Okay, so there are several thin film deposition techniques were employed to grow these thin films. So generally, the uh, preparation of these thin films can be done with two different techniques we have, like a physical vapor deposition method is there, and as well as the chemical vapor deposition method is there. So under this physical vapor deposition method, we have different types of methods are there, and as well as in the case of the chemical vapor deposition, also we have different types of methods are there. So if you take this physical vapor deposition method, it is well established technique which is used to deposit high quality thin films. Okay, high quality thin films. In order to prepare, we'll use this physical vapor deposition method, and they can be deposited. Uh, Deposit the film can be used. The deposited film can be used for what we call variety of applications. We'll be using. So this is the versatile technique, physical vapor deposition method, where wide range of materials like refractory materials, elements, mixtures, and alloys can be deposited. Okay, and this method, that is physical vapor deposition method, under that we have like a electron beam evaporation technique is there, as well as the pulse laser deposition technique is there, magnetron sputtering. All these comes under this what we call this physical vapor deposition methods only. Another type of method in order to prepare these thin films is chemical vapor deposition method. So under this chemical vapor deposition method, we have uh, the main methods which we have is sol gel deposition method is there. That is one method under chemical vapor deposition. Another one is pre-pyrolysis deposition method. Another one is a chemical vapor deposition method. So these are the three different methods which we have under the chemical vapor deposition. Mainly, they are classified into the preparation methods are classified into physical vapor deposition method one type. Another one is a chemical vapor deposition method. Okay, these are the two types of thin film preparation. So this thin film is mainly used, as I told, in many applications.